Welcome to this video on what is radiation. Okay, I'm going to split radiation into two parts, but let's look at the textbook definition, a definition I found on the internet. The emission of energy as electromagnetic waves or as moving subatomic particles, especially high energy particles which cause ionization. That might make sense to you, it might not. Either way, I'm going to try and sort of simplify it a little bit. So as I said, I'm going to split it into two. I'm going to split it into electromagnetic radiation. Now, electromagnetic radiation, this is an energy transfer in the form of waves like microwaves or infrared, visible light, and so on. I'm not going to spend any more time on this because I've made a video on it. All you need to do is click on the link above and you can find out lots more about electromagnetic radiation. The other type is nuclear radiation, so called because it comes from the nucleus of the atom. Now at this point, if you haven't studied the structure of an atom, stop this video, click on this link and watch the video called How to Draw an Atom. If you don't know your way around an atom, then some of this stuff might not make sense. If you do, if you know about atoms and protons and neutrons and electrons and how they're all arranged in an atom, then we can go ahead now and talk about alpha, beta and gamma radiation. So, starting with alpha. In alpha radiation, you have an unstable nucleus, and this unstable nucleus fires off a lump, and this lump is made of 2 protons and 2 neutrons, so it has a mass of 4. And that is exactly the same as the nucleus of a helium atom, hence the He next to the alpha particle. Now this alpha particle flies through the air, collides with other atoms, causing ionization, and we'll talk a little bit later on about what ionization is. Now look at the daughter nucleus. The total mass has changed. What's happened? It's gone from 238 down to 234, so the relative atomic mass has gone down by 4 because it's lost 4 bits. The proton number has gone down by 2 because it's lost 2 protons. So it's changed from uranium to thorium. And that's what happens when you get alpha decay. By atomic terms, alpha particles are big. They're a big lump, like a cannonball. It's highly ionizing, highly damaging, but it's not very penetrating. It wouldn't go through a piece of paper. So if you wanted to hurt someone with an alpha source, you'd have to either feed it to them or inject it into them. So it's really not very penetrating at all. Now, before I give you an example of how alpha radiation is used, I want to explain ionization to you. So you get this high energy radiation, like this alpha particle, flying through the air. It smashes into an atom, like, I don't know, like something in the air, nitrogen, oxygen, and it knocks an electron off. And if it knocks an electron off, if you remember, electrons are negatively charged. So if you lose an electron, you're going to become positive. You become a positive ion. We don't call it an atom anymore. It's now an ion. So the radiation smashes into a molecule or an atom, knocks an electron off or 2, and we have a positive ion formed. It could knock a proton off, and if it did that, you've lost a positive. And if an atom loses a positive, it's going to become a negative ion. So have a look at the magnesium atom in the corner of this slide. It loses 2 electrons in its outer shell, and therefore it becomes a 2+ ion. So here we are. Let's look at one use of alpha radiation. It's being used here in a smoke alarm. We've got a positively charged plate at the top and a negatively charged plate at the bottom. And we've got ionization events going on. The alpha particles are flying through the air, smashing into the molecules, knocking electrons off and leaving positive ions. So we've got positive and negative ions in this gap between the positive and negative plate. Opposites attract, so the negatives will move up to the positive charged plate and the positives will move down to the negative charged plate. And the effect this has is to keep the current flowing and flowing and flowing. Now, let's say you get smoke in between these 2 charged plates. What's going to happen? Well, smoke is enough to block the alpha particles. It doesn't take very much. If they block the alpha particles, there's no ionization because they're not colliding with the air particles, the air molecules. No electrons formed, no ions formed, and therefore the current stops. And if the current stops, the alarm goes off. It's quite possible as well that the individual little smoke particles are absorbing the ions. If there are any ionization events, those electrons and positively charged ions are actually joining with the smoke particles, so they're not getting to the charged plates. Either way, the current stops. The flowing current stops, and that sends a signal to sound the alarm. So you want a current, a continuous current, and you're going to use an alpha source for this. In beta decay, a neutron in the nucleus turns into a proton and an electron. Okay, a neutron actually physically turns into a proton and an electron. The proton stays where it is, stays in the nucleus, and the electron is fired out of the atom. So the mass number stays the same. A neutron weighing 1 has turned into a proton, which also weighs 1, so no change in the mass number. But the bottom number, the proton number, that has to go up by 1 because we've gained an extra proton. So that's beta radiation. Beta particle. A beta particle is fairly penetrating, moderately penetrating, and moderately ionizing as well. So let's talk about one of the uses of beta radiation. In the manufacture of aluminium foil, or aluminum foil if you're in the States, is a good example of a use of beta radiation. A radioactive source is placed above the foil and a detector below it, and if too much of this beta radiation is reaching the detector, that means the foil is too thin. So it sends a signal off to the rollers to reduce the pressure, don't squeeze so hard, and that causes the foil to get thicker. Now, if too little radiation is being detected, there's not enough radiation coming through, that means that the foil must be getting thick, and you send a message to the rollers to apply more pressure, and the foil gets thinner. So the foil stays within a certain boundary, a certain sort of thickness throughout, and that's one use of beta radiation. Finally, gamma radiation. This is a high frequency electromagnetic wave. There are no protons, neutrons or electrons involved. It's just a wave. So the mass and the proton number both stay the same. Having said that, there is still enough energy in a gamma ray to cause an ionization. Okay, so then in gamma radiation, the numbers don't change one bit, but it's still ionizing, it's still damaging. If, you know, when a nuclear bomb gets dropped, if you don't die in the blast, then and if you're anywhere near it, you may well be irradiated. You may well have some genetic mutations caused by gamma radiation from a nuclear blast or something like that. Gamma is the most penetrating of them all. It takes thick lead or thick concrete to stop it. However, it is the least ionizing of the nuclear radiations. Compared to other EM waves, compared to infrared and the other waves, it is very ionizing, but as I say, not compared to alpha, beta and gamma. It's the least ionizing of the three. One use of gamma radiation is in sterilization, so we can sterilize surgical equipment or even our own food. With a blast of gamma rays, we know that there'll be no bacteria or fungus causing a decay and causing all that nasty food spoilage, so we can use it for sterilization. Okay, there we are, a very quick run through of the different types of radiation: alpha, beta and gamma, nuclear radiation and EM radiation as well. I hope that was useful to you. Have a go at these questions. Pause the video now, write some answers down, and I will change the slide and the answers will flash up in a second. If you know someone else who's going to benefit from a video like this, then hit the share button, and thank you very much for watching.